Welcome once again all of you. Today we will have that session of physics for class 11th. You may have seen that in this session we are going to study about the Newton's laws of motion. And we will have that idea of that frame of references and pseudo force as well. So we shall start that by saying that what is physics first. We should know. So physics is the branch of science that deals with matter and energy, and their interactions Okay, so the branch of science that deals with matter and energy and their interaction will be called as our physics. In general, people say that study of the nature is that physics. So you will remember this, you can have the idea of study of nature as well. So that Newton's laws of motion and other sessions we will have in that classical mechanics, and it is present in your course, that classical mechanics. When you will go to the higher classes you will have that other mechanics as well, but that classical mechanics we will have in our course. And that what is classical mechanics, and that we will first know that classical mechanics is the branch of physics. It is the branch of physics that investigate the motion of the objects in our daily life. So that branch of physics that investigating that motion of objects will be called as our classical mechanics. And what is physics? I have written there. You can have the screenshots of it. I am rubbing. Now student, that this classical mechanics, we have seen that it is the branch of physics, and in this we will investigate the motion of objects in our daily life, and that is, I think, important to know. So this classical mechanics we can that divide into the two parts, that is our static and dynamic. Static means that objects are at the rest. Dynamic, objects are moving. Then this dynamic we will subdivide into the two parts, and that will be our kinematics and kinetics. Okay, one is kinematics and other is the kinetics. In kinematics we will say that how the objects move. Whereas in that kinetics we will say that what are the causes of motion. What are the causes of motion. So in kinematics, we will not consider the cause of motion, whereas in kinetics we will have the what are the causes of motion. So this thing you will keep in your mind, that kinematics, that we are not saying that what are the cause of motion. We are only focusing that means how the objects are moving. Now, means why the objects are moving we are not considering. But in kinetics we will also consider that why the objects are moving. So example we can have that in kinematics, that you know that position, velocity, acceleration, etc. Okay? So example of kinematics can be position, velocity, acceleration, etc. Kinetics, that example of kinetics can be that friction, torque. This we will say that as our kinetics. And kinematics, that position, velocity, acceleration, this thing will tell that how that objects are moving. And this kinetics, that in this we will consider that why that objects are moving. So I think the idea of this that static, dynamic, and that kinematics and kinetics you can have before going to the detail. Can I have this screenshot of it? So we are going to study the laws of motion, so that we should also know that what is motion. Motion, what is motion? Change of position, please. Change of position. This position is very important. Now you are in that 11th class, and miss, how are you defining the position is the matters. That change of position with respect to time. I think so means that you guys will have that idea of position. You might have that heard about that position in your 9th class. Once again I am recapitulating that if the change of position with respect to the time is taking place, we will say that object is in motion. So what is position, student? So to define the position, what we should have? For defining the position, we should have certain length and direction as well. Length, direction, and other thing we can say that point of reference. Point of reference. In the very simple way we can think that suppose I am asking you that where is that Mubarake Kila, that red fort, you know, that is also called as your Mubarake Kila. You know that PM is in that red fort. Where it is present? You will say what is the position of that red fort? That is it that Raisina Hills? No. If someone is saying to you that what is the position of that red fort, you will say that it is present that if anyone is asking that where is that red fort, so if you are saying that go to the Raisina Hills, so Raisina Hills, how will he go? You will have to be defined now that Raisina Hills is present at this much of that length. Next question he can ask to you that okay, you have told to me that at this length Raisina Hills is present, there I will have that red fort. So that Raisina Hills at this length is present in which direction? So that you will also have to be defined that direction of that. And after knowing it, he can also have the question that okay, you have told to me that at this much of the length that our red fort present at that Racina Hills is present. So at what point I will measure that length? Whether I will measure from here or from that here or from here. So that also, that point, from which point you are saying that length, that is also important to know. So that idea of this I have given to you. You can remember that for that defining the position, that we will have that length, direction and point of reference. So we have seen that motion and this position. You will keep in your mind that it is not going to left you in classical mechanics. And next thing, we can define that rest. What is rest? If you will say that if the position of objects remains same with respect to time, isn't this will be rest? Whether it will be rest, that if the position of object with respect to the time, we are saying that it is our rest position. No, you are in 11th class. You will also have to be say that keeping the reference point same, keeping a fixed point of reference, isn't? Means until you are not saying this, our point of reference is fixed, the rest will be not defined. That you can have that, means you may have heard that rest. If a book is kept on the table from the earth or from this room, I am that looking, that book is at the rest. But if I am going to the moon, that earth is rotating, so that from moon it will be not at the rest position. So while are we defining that rest, we will keep in your mind that keeping the reference point same until you are not saying this. If the position of objects remains same with respect to the time, keeping the fixed point of reference, that rest will be not completely defined. So you can have the screenshot of it. So we have moved to the motion and rest, and we are studying that kinematics. That laws of motion will come in that category of kinematics. So that you will keep in your mind. Next thing is very important to know what is force. So force, you can define that push and pull effect is called as our force. So for the time we are studying that classical mechanics, so I am firstly defining it in the terms of mechanics. It is that mechanical interactions of material bodies. Mechanical interactions of material bodies. Next thing is very important to know. How many of you are aware about it? That force will have that magnitude, require three things. It requires how many things? Three things. That magnitude, direction, and what is the third thing? Third thing is your point of application. At which point you are applying the force. Means if I have the beam somewhere, means that it is our beam, whether I am applying this force at this point or this point, we will have the different kind of motion, isn't? So that point of application is also important in our force. Not important that we will say that point of application in that force, then only that force is going to be finished. So that you will keep in your mind that it will have that three things: magnitude, direction and point of application. And next thing you will keep in your mind that force can arise in two ways, we can say. When the objects are in contact, and next thing we can define that when the objects are not in contact, isn't? That force can arise when the objects are in contact. Suppose I am that applying a force on it, that board. So what means I will feel means that board is applying some force on my palm, and at the same time my palm is also applying the force on that board. So here the interaction of that palm and board is taking place, so that when the objects will be in that contact, that force can arise. Next thing, what I am doing, that I am dropping this chalk. So it's going down. I am dropping this chalk, that it's going down. So is it there interaction, or that is it there that contact between this, and when it is going to the earth, is there any contact? No contact. So it is going because of the force of gravity, you can say. So here you will remember there is no that contact present in that bodies, but the force is arising. And next thing, that when I am applying a push on that board, my palm will feel some kind of the force, and at the same time that I am also applying a force on the board. Very important for that numerical point of view test. These are the basics I am telling to you. And if your basics will be not strong, you will feel problems in your physics. So these points, just note down it, and this will be the weapons to solve the numerical problem. We will move to that, but before that I want to give my language of physics, and I am starting from that laws of motion, because other chapters, that motion in 1 dimension, 2 dimension and units, and that I will tell you that. Don't worry about that. First come to this. So we have seen that force, and that force can arise that when it is in contact or not in contact. And next thing you will that keep in your mind is that force is a vector quantity. You may have heard about the scalar and vector quantity in your 9th class. Force is a vector quantity and require both magnitude and direction. You can say that, Miss, why not that point of application? Please, no. While are we saying that it is vector quantity, then I am saying that magnitude and direction. But you will also keep that at which point that we are applying the force. I have told you. So force is a vector quantity which require both magnitude and direction. It is represented by an arrow on the top of it. That is in this way. Capital F is saying that it is force, and we will put the arrow on the top of it, and length of arrow tells magnitude of force, and the direction of arrow tells the direction of force. Is it? So this force will be there, vector representation, vector quantity, scalar quantity, I will tell to you. But for the time, recall that vector quantity in general we represent in this way, by an arrow, by this, that an arrow we will make, and some length we will make, and we will have that parallelogram of vector addition, triangle law of vector addition. So this will be here. So I will tell about that, but for the time only up to here. And you can note that since force is a vector quantity, so we can apply the parallelogram and triangle law of vector addition. Is it? So we can apply the parallelogram law of vector addition, triangle law of vector addition on it. When the different forces will have the different direction, we can apply that. So I have this screenshot. Next we shall move to the frame of reference. This frame of reference, we can abbreviate it as our FOR. So this frame of reference, we can have the idea from the very common example that suppose I am moving in a train. So I am in the train and the train is moving, and when I will look outside, that I will look that train, that trees, poles, buildings are moving. And let you are at the ground and looking that it's not the trees, poles, buildings are moving, it's the train is. So I have that appearance of moving building, trees and poles, and you have that appearance of movement of train, not the trees, building and poles. So from the different frame of reference, things has got changed. So it is the general way of understanding the frame of reference. We will talk more about it. First, what is that frame of reference? That frame of reference is that coordinate system in space. Coordinate means that we all are aware about it that we have that x coordinate, y coordinate, z coordinate. So that coordinate system in space along with that time system, we can say as our frame of reference. So frame of reference will be of two types. That one will be called as our inertial frame of reference. Second one we can say as our non-inertial frame of reference. Inertial and non-inertial frame of reference. So what is an inertial frame of reference? Inertial frame of reference is that frame of reference at rest. So frame of reference at rest or moving with uniform velocity. So if a frame of reference is at rest or moving with uniform velocity, that we will say as our inertial frame of reference. Uniform velocity, student, that what's the meaning of that uniform velocity? Recall the 9th class that uniform velocity that will have acceleration equals to 0. For that uniform velocity, there will be no acceleration. So our inertial frame of reference will not move by any acceleration. It will only move with uniform velocity or it will be at rest. Non-inertial frame of reference is that frame of reference with an acceleration. Or that we will say that frame of reference moving with an acceleration. So if a frame of reference will move with an acceleration, that will be called as our non-inertial frame of reference, and here you are looking that acceleration is not equals to 0 in the case of that non-inertial frame of reference. So that inertial frame of reference can be at rest or it can move with that uniform velocity. The meaning of that uniform velocity is that it will have no acceleration, whereas that non-inertial frame of reference will have some acceleration, and the accelerated frame of reference will be called as our non-inertial frame of reference. Next point of note is that Newton's laws of motion are applicable in inertial frame of reference. So that Newton's laws of motion will be applicable in inertial frame of reference, whereas that Newton's laws of motion for that non-inertial frame will be not applicable. So for a non-inertial frame of reference, we guys are looking that we can't apply that Newton's laws of motion in that. And Newton's laws of motion will be applicable only for that inertial frame of reference. And what is that inertial frame of reference? So that frame of reference at rest or moving with uniform velocity, and non-inertial frame of reference will move with certain acceleration. So if a frame of reference is moving with certain acceleration, we cannot apply the Newton's laws of motion in that frame of reference. So note up to here, you can have the screenshot of it and we will talk more about it. Now come to the inertial frame of reference. This is our inertial frame of reference. Inertial frame of reference, we can have the idea by a car. Suppose we have the car here. And it is moving with uniform velocity. So moving with uniform velocity, acceleration is 0 in this case. So that car is not accelerating, it is moving with uniform velocity. And suppose in the car you and your friend is traveling. You and your friend is going, and here we can have that driver as well. And you guys are playing ball catch. You are throwing the ball to your friend and your friend is catching that ball. Again, your friend is throwing the ball to your lap and you are catching. Like this, you guys are doing a task of catch of ball in a car which is moving with uniform acceleration. So here, student, we will look that this catch play will take place without any disturbance. That you and your friend can have the play of catch that easily, it will not disturb anything to that play of catch. Here, that inertia of the ball, means inertia will hold good, means in other way we can say that while we are throwing the ball, we are applying the force, your friend is catching the ball. These are the examples of Newton's laws of motion, and that will be applicable here when it is moving with uniform velocity. So since that inertia holds good here, so it will be called as our inertial frame of reference. So if the car will start accelerating, you will look that this play of catch will have some disturbance and it will not take place easily. That ball will go somewhere else. If you are thinking to have the ball here, it will go here, or it may miss. If you are thinking to ball here, it will go back to you. So that will take place when that car will accelerate, but when it is moving with uniform velocity, means having no acceleration, so this catch play can take place without any disturbance. So it will be an example of inertial frame of reference, since that Newton's laws we are applying here is applicable and it is holding good in it. Next we will see that example of that non-inertial frame of reference. So for that non-inertial frame of reference, we are saying that suppose this car is here and this car is moving with certain acceleration. That car moving with acceleration A, you can say. So you can think of a bob connected with that string or that pendulum hand in that car will make certain angle theta with vertical direction when the car will accelerate. So when that car will accelerate, this bob which will be at that vertical position while it will move that with uniform velocity will make certain angle when will it start moving with certain acceleration. So when that car is moving with acceleration A, it is making certain angle from the vertical, and that is our theta. And you are present here and you are observing this bob string, that arrangement, or you can say that pendulum you are observing. You can have that driver as well here. We will not talk about that. So you are observing the bob, and when that car is accelerating and this pendulum is making certain angle with vertical, what are the different forces acting on this bob? Pendulum. That here, that mass of that bob will have the weight mg, which will act in that downward direction due to the gravity. That weight of bob will be mg, will act in that downward direction, and tension in that string of that pendulum will take place, and that tension will be along the string, and it will have that pulling effect. So these only two forces, that weight of that bob and tension in that string, are present here. No other forces are acting on it. So here you are looking that this kind of that triangle we are getting, and here is that angle theta, and here that mg is acting, and tension in that string is here. Of course this will be our 90. On this side we are having the two angle, so this will be our base, this will be our perpendicular. And when you will resolve this tension in horizontal and vertical direction, you will have that tension cosine theta means t cos theta along this direction and t sine theta in this direction. So when are we resolving this tension here, we can say that t cos theta, no, t sine theta will come here, t sine theta is acting here and t cos theta, we have shifted this t cos theta here, here we can say this is here, so this t sine theta is t cos theta is acting here. So we have the t sine theta here, t cos theta here. So this t cos theta will get balanced by the weight of that bob. Still we will have t sine theta in this direction. So you are looking that t sine theta is acting in this direction. So this bob should go to the vertical, but it will not go to the vertical. Look, that car is that moving with certain acceleration, it will make some angle. It will that form the angle. Means that until it is accelerating, it will have this angle. So it is having the angle and a force is acting here. So you are looking that when this force will act here, so that this bob should accelerate, but whether is it accelerating? No, it is not accelerating, it is at the same position, that at theta angle it is present. It is not accelerating, it is at the same position when that car is accelerating, but a force is acting here, which is that this we have balanced, this t sine theta is not balanced. So we are looking that a force is acting, that force is not equal to 0, but acceleration is 0. This first point we can say that force is not 0 on this bob, this t sine theta is acting here, but that our bob is not accelerating, it is at the same situation with theta angle with vertical. So we can think that t sine theta is acting here, so we can apply some force in this direction to make this t sine theta 0. A force is acting here, t sine theta, so we can think to make it 0 by applying some force in that other direction. So when you will apply the force to make this force equals to 0, that bob will start accelerating. Means when it is accelerating, making this angle, no force you are applying, still a net force is acting on it and that bob is not accelerating. So you can think that since a force is acting here, so we can make this force equals to 0 by applying some force in that opposite direction, and when you will apply the force, this bob will start accelerating. So second case you can have that when this force you are making equals to 0, force this t sine theta you are making equal to 0 by applying some force in that opposite direction, your bob will start accelerating and that acceleration will be not equals to 0 in that case. Is it? So what is Newton's first law? Newton's first law. Newton's first law says that an object will be at the rest or in that moving situation until and unless that a force is not applying on it, that when that force equals to 0, that acceleration will be equals to 0, or when are you applying some force, so it will accelerate. It is the only Newton's first law. Whether it is following here, F is 0, but our acceleration is not 0 here. In the same way, you can say that when the force we are applying on any object, it will start moving. That is also not happening. F is 0, but acceleration is not 0. So whether that Newton's laws are applicable here. So you are looking that Newton's laws of motion, are not applicable. So Newton's laws of motion are not applicable here, and it is because it is the non-inertial frame of reference which is moving with certain acceleration. Try to understand it, think about it. Repeat this video by going back 2-3 times. You will have that assumption of it. We will prove in numerical way as well this inertial and non-inertial frame of reference. These were the example, you can say. So we shall start the numerical proof of that frame of reference. Frame of reference, I have discussed that it's the coordinate system in space with that time system as well. So we are considering a coordinate system x, y, z. So our x coordinate, y coordinate and z coordinate, calling as frame S, and another coordinate we are considering as our this x prime, y prime and z prime, calling as frame S prime. So frame S prime is parallel to frame S, but it is shifted. It is shifted, but it is parallel to the frame S. It is not rotating. It can rotate as well, but for the convenience that we are saying that it is parallel. And an observer 1, we can say observer 1 present at the origin of frame S, and observer 2, this observer 2 is present at the origin of frame S prime, looking to an object placed in that frame S. So when that observer is looking to that object from frame S, observer 1 is finding the position of that object as r, small r vector, and when this observer 2 is observing the position of object from frame S prime. He is finding the position R prime vector of that object, and these two observers have the relative position vectors, to which we are denoting by capital R. So we can write this, that small r is representing that position of object, position of an object R vector is representing the position of an object observed by observer, I am abbreviating, observer 1 from frame S, and this small r prime vector is representing the position of object 2, not object 2, I'm sorry, position of object observed by, is representing that position of object observed by observer 2 from frame S prime, and this capital R is representing the relative position vector of object 1 of observer, not object, observer 1, observer OB I am writing, observer 1 and observer 2 in frame S and S prime respectively, you can say, respectively. So this, we are considering a frame. So for frame we will have that coordinate system. So that x, y, z coordinate system we are saying as our frame S, and x prime, y prime and z prime we are saying as our frame S prime, and observer 1 is present at the origin of that frame S and observer 2 is present at the origin of frame S prime. Looking to an object present in that frame S, and observer is finding the position vector small r vector, observer 2 is finding the position that small r prime vector, and this capital R is representing that relative positions of that observers in that frame S and frame S prime. But this S prime frame is parallel, but it is shifted, it's not rotating, whereas it can rotate as well. So note up to here. Can I have the screenshot? So we have seen that position vectors of that object from frame S and from frame S prime. So we can say that from the geometry of the position vectors, here we are getting a geometry that position of that object observed by observer 1, which is denoted by that small r vector will become equal to that this capital R vector plus small r prime vector. From triangle law, when will I give you that video of that vectors? So from there we will talk. You can recall that 9th class. From the geometry, this resultant will be nothing but the sum of these two. So this our R vector will become this R prime vector plus capital R vector. And now suppose we are saying that when frame S prime is moving with constant velocity, not when, you can say let frame S prime is moving with constant velocity, capital V vector. So this capital V is that capital V vector is that velocity of frame S prime with respect to frame S. So this our frame S prime is moving with that constant velocity and having the coordinates x prime, y prime and z prime here. It has moved here now. So our frame S prime and observer 2 is present at that origin of frame S prime, will look to that object and will find the position vector different from the first situation, and also that relative position of the observer in frame S and frame S prime will get changed, and it will become the function of time. This R prime vector also become the function of time when it will move, and we can say that our this small r vector is not the vector is not the function of time, but it will be not the function of time when we will look from the frame S. When we will look from the frame S prime, which is moving with constant velocity, it will also become the function of time. Okay, so note up to here, and frame M E will be here. So you can have the screenshot. After that I am telling to you. So we have seen that capital V vector is representing the constant velocity of that frame S prime with respect to the frame S, and we have seen that when it is moving with constant velocity, that capital R vector and this small r prime vector is also becoming that function of time, and when will we look to this position vector from frame S prime, it will also become the function of time. So recall that we were getting that small r prime vector equals to that small r vector minus of that capital R vector. So it's the position of that object from frame S and from frame S prime. So what will be that velocity of that object from frame S and from frame S prime? For that we will differentiate it, and if you are that in 11th class you will be not aware about this differentiation. If you are aware, it's very good. Differentiation is, student, it's a change, some change, small, very little change, it's taking place with respect to some other thing. So here we are considering that change is taking place with respect to the time. So we will say that differentiating with respect to time. So when will we differentiate it with respect to the time, we'll get this. This differentiation of that position of the object from frame S prime with respect to the time, and change of that differentiation means change. Differentiation of that small r vector from the frame, that position of that object from the frame S with respect to the time, minus of that differentiation of that position, relative positions of that frame of the observers from frame S and from frame S prime. We are differentiating with respect to the time. So that differentiation is telling us that change. So change means what? Look, student, that change in position divided by change in time. So change in position divided by change in time will be called what? Will be called as our velocity. So this will represent this velocity of that object in frame S prime will become that velocity of the object in frame S minus times this differentiation of that relative positions of that observers with respect to time will give us what? That velocity of frame S prime with respect to that frame S. Is it? So we will get this expression, and you can note down that it's nothing but the velocity of the object from frame S prime. It's the velocity of object from frame S minus times the velocity of frame S prime with respect to frame S. That meaning is that whatever velocity we will have from the frame S prime of that object, that will be equals to that velocity of the object from frame S minus times the velocity of the frame S prime from which we are looking to that object. So when that frame S prime is moving, so velocity of that object from frame S prime is coming equals to the velocity of that object from frame S minus times the velocity of that frame S prime with which it is moving. Suppose that our object is not moving in frame S, it is at the rest position, so this V will become 0 here. So when this V will become 0 and our frame S prime is moving with constant velocity capital V, so what will be that velocity of that object from frame S prime? That will be equals to nothing but the velocity of that frame. But negative sign will tell that it will be in opposite direction, isn't? So it is that velocity vector. So if that I am in the train moving with certain velocity, building, I am looking outside, so building is that at rest, the velocity of that with respect to that an observer from the ground, it is looking that velocity is 0. So I will appear the building is moving in opposite direction with same velocity with the train is moving, isn't? If I am in the train moving with certain velocity, I will appear that building is moving with that same velocity but in that opposite direction. So that when that velocity in that frame will be 0, so that velocity in that frame S prime will become that velocity of that frame S prime with respect to that frame S but in opposite direction. And if that something is moving in that frame S, so that velocity of that object when it is moving with certain velocity, we can say v, small v vector, and we are looking from frame S prime, so that will become, so velocity of that object from frame S prime will become that velocity of that object from frame S minus times the velocity of that frame with it is moving. So a concept of that relative velocity we will get from here. You can note down up to here, after that I am telling to you. Can I have the screenshot of it? So we have got the expression of that velocity of that object in frame S prime, that was equal to that velocity of that object in frame S minus times the velocity of the frame with which it was moving. So we have got the expression of that velocity. We can also think about the expression of that acceleration of that object from frame S and from frame S prime. So that acceleration, for that acceleration, what will we do? Again differentiating with respect to time. Why are we that again differentiating it? Differentiating d is that very little change we are doing. Divided by dt means that with respect to the time. So that change in velocity divided by change in time will become that our acceleration. So that when we again differentiate it, it will be that d by dt of that small v prime vector will be equal to d by dt of that small v vector minus d by dt of capital V vector. One thing you guys will keep in your mind, that differentiation of constant is equal to 0. Means that when you will go to that differentiation, it will tell, this chapter will tell that if you are differentiating some constant, means 5, 10, 50, 500, so that if you are differentiating some constant value, so that will be equal to 0, and applying this in here, we will say this expression, this derivative of that capital V vector with respect to the time will become 0, since our velocity is constant. This capital V is the constant velocity of that frame S prime. So this will become equal to 0, and here we will get the expression that it is nothing but our change in velocity divided by change in time. So that is acceleration. So that small a prime vector will become equal to small a vector. What is the small a prime vector? It is that acceleration of object in frame S prime, and this is the acceleration of object in frame S. In frame S. You can have this screenshot. I am rubbing upside. So we are getting the identical acceleration, same acceleration of that object, whether are we considering the frame S prime or S. The acceleration are coming same. Next thing, what will we do? That multiplying by the mass of the object both sides. Let small m is that mass of the object that we are multiplying both sides. So this will become mass times the small a prime vector, mass times the small a vector. And what is this? Mass times the small a prime vector, mass into acceleration of the object. So that force, this capital F prime vector, will become equal to capital F vector. It is the force on that object from frame S prime, and it is the force of the force on that object from the frame S. So both the frame from that frame S prime and frame S are coming identical. Why it is coming identical? Because that acceleration is coming identical. Although our that velocity and that position was different from that frame S and frame S prime, our acceleration and hence that force on that object will be same, whether are we considering the frame S or frame S prime. So when this force is same on that object, so Newton's law is applicable here, because that force from the frame S prime and force from the frame S both are coming same. So it will be our inertial frame of reference. Okay. So we have seen that the forces are coming identical from two frame of reference, even though the velocity and position is different for two frame of reference. Although our velocity and position are different for that two frame of reference, our force are coming identical because that acceleration is identical. Hence that frame of reference is inertial frame of reference, and Newton's laws of motion are applicable. Now let the frame S prime is not moving with constant velocity and accelerating with the acceleration of capital A vector. You can have the screenshot quickly. I am rubbing upside. So now we are saying that capital A as the acceleration of frame S prime, and our velocity is not constant in this case. So recall that expression which were we getting this del v prime vector of that with respect to del t divide dt of that small v vector minus of this del capital V vector divided by del t. This will become this small a prime vector equal to this small a vector minus of that capital A vector. Is it? Change in velocity divided by change in time is acceleration. And here this expression was coming equal to 0 in the case when that frame S prime was not moving, when the frame S prime was moving with constant velocity. So that differentiation of that constant will be equal to 0. But here in this case, since that velocity is not constant, it is moving with certain acceleration. So it is not a constant, it is varying. So that change in velocity divided by change in time is nothing but the acceleration, and that acceleration we are saying as our acceleration of frame S prime capital A vector. Okay? Now next thing is that multiplying both sides by the mass of object. So when you will multiply the mass both sides, the expression you guys will get this mass, this will be A prime, small a prime vector, mass we can cancel, and the same expression we will get, and this is going to give us m times the small a prime vector equal to m times the small a vector minus m times the capital A vector. And this what mass into acceleration is nothing but our force, and this capital F prime vector will be equal to that capital F vector minus m times the capital A vector. Is it? Now we are looking that forces are not coming identical, and the frame of reference will become non-inertial frame of reference. So right up to here, you can have this screenshot up to here. This capital F prime vector is representing that force on object from frame S prime, it is representing that force on object from frame S. And what is it? This is the force from the frame S prime. This is the force from frame S. And what this m times that capital A vector is coming. This we will call as our fictitious force. This we will call as our fictitious force, or in general we also say it as our pseudo force. Pseudo force. This fictitious force, that apparent force which is acting here, that we can also term as our pseudo force. You will be aware about it, pseudo force. So why we are saying this as our fictitious force? Here you guys are looking, this is representing the mass of object, isn't it? And it is representing the acceleration of frame S prime, isn't it? So mass of object we are multiplying with that acceleration of frame S prime. So something that something is that there which will be not able to say some force, but for the sake that if that m times that capital A acceleration that m times acceleration will give us some force, so that force we are saying as our fictitious force, pseudo force. And why we are saying it as our fictitious force? Because we are multiplying the mass of the object with the acceleration of frame S prime. We are not multiplying that mass of the object with that acceleration of that object. We are multiplying with that acceleration of frame S prime. So a fictitious force will come there, which will that subtracted from that force present in that force on that object from frame S, and that will be called as our pseudo force. And you will look that forces are not coming same from frame S and frame S prime. So force on object is not identical from frame S and S prime respectively. And we cannot apply Newton's laws of motion when I'm writing here frame S prime is accelerating. Isn't? Forces are not coming same. Whatever will be that force from frame S prime, that will be that force on the object from frame S minus times this fictitious force. As pseudo force we will have to be subtracted from that then only this will become equal, and for this expression we will say that forces are not coming same. We will have to be subtract some force from that. That is our apparent force. So that forces are not identical in that both frame of reference, and when that frame is accelerating with certain acceleration, so it will become that non-inertial frame of reference. It will become our non-inertial frame of reference. I have given you that idea that what will be a non-inertial frame of reference. Newton's laws will be not applicable in that, and we are looking that forces are not coming same. And for that, and that non-inertial frame will move with certain acceleration, and when we have considered that acceleration of frame S prime, we are looking that forces are not coming same. Whereas for that inertial frame of reference, when we have seen that when it was moving with constant velocity, it can be at rest as well, but when it was moving that constant velocity, forces were coming same, and that was our inertial frame of reference. So we'll define pseudo force. Pseudo force is a fictitious force which we add in non-inertial frame of reference, to make it inertial frame of reference, and Newton's laws of motion to be valid. We cannot apply the Newton's laws of motion for non-inertial frame of reference. So a pseudo force, this pseudo force we are saying mass of that object multiplied by that acceleration of that frame S prime, that pseudo force, when we will add in it this, so this pseudo force mass times the mass of the object times the acceleration of frame S prime, pseudo force, a fictitious force, when will be add in non-inertial frame of reference, so that minus m times capital A vector plus m times capital A vector will get cancelled out, and we will get that force on that object from frame S prime and force on that object from frame S identical when we will add a pseudo force in it, and it is our non-inertial frame of reference, and that non-inertial frame of reference we can make an inertial frame of reference only when we are adding a pseudo force on it. One thing you guys will note down, that pseudo force we will always apply in opposite direction of the acceleration of frame of reference. means in whatever direction that our frame of reference will accelerate, opposite to that we will apply a pseudo force. An example I have given to you, when that car was moving with certain acceleration, that our pendulum was making certain angle, and we have seen that net force was acting on that, and that will become that non-inertial frame of reference, because that a net force was acting there, and that net force we can make equal, it was acting t sin theta in this direction, so that was that non-inertial frame of reference. So in that, if that applying a pseudo force in opposite direction, so that force will get balanced out, and that non-inertial frame of reference will become inertial frame of reference, and we can apply the Newton's laws of motion in that. So from here we will get the idea of pseudo force. Pseudo force we apply in that non-inertial frame of reference to make that inertial frame of reference, and to make the Newton's laws of motion applicable in that, and that pseudo force we will apply in opposite direction of that acceleration of frame of reference. It's important for that numerical point of view, opposite direction to the acceleration of frame of reference. So this thing you guys will keep in your mind, and numericals based on it will be asked in so many exams. We will solve the numerical based on it. When will we have that session of numerical? I am giving the first video and starting with Newton's laws of motion. So before that, this must come in your mind to move to the Newton's laws of motion, and we will have more videos. You guys will be aware about it. Numerical proof of that inertial and non-inertial I have given to you. That examples also I have given to you. Numerical proof I have given to you. Go to it 2, 3, 4 times and try to understand it. Numerical when will be solved, you will have that better idea of it. Okay, can I have the screenshot of it? So here we have that question here, that whether force depend on that frame of reference or not. That our answer will be no. It's only the position, velocity and acceleration which will depend on frame of reference. Force will be same in every frame of reference. Okay, so this thing you guys will keep in your mind, that force is not going to depend on that frame of reference. It is only the position, velocity and acceleration which will depend on that frame of reference. Okay, so you can have that acceleration and reasoning, and there they can ask you that whether that force will depend upon that frame of reference or not. Your answer will be no. Obviously that coordinate system position, when are we saying that we will have that x coordinate, y coordinate, z coordinate, so that position will depend upon that frame of reference, and if that position is depending, so velocity and acceleration will depend, but our force is not going to depend on that frame of reference. So this thing you guys will keep in your mind, and it was that Einstein who introduced the non-inertial frame of reference, we can say. and that only the idea of it we will not go to the Einstein and that Einstein it's the theory of relativity, it's the other class of that physics, it's the class of that classical mechanics only present in our course, so that we will that have the inertial frame only. And why we have studied the non-inertial frame of reference? Because some introduction of it is present in your course and we will have that problem based on that also. So that it's the classical mechanics we shall start. So we are arranging the things now which we should know to move for that laws of motion. Okay. So we shall start the class of that classical mechanics. That classical mechanics, that in classical mechanics that we will consider the speed of the objects much lower than the speed of light. So our speed of the objects will be very much less than the speed of the light in that our classical mechanics. And when we are considering that speed of light, theory of relativity will start coming, and that is not present in our course. Okay. But this pseudo force is present. Pseudo force, that introduction of that theory of relativity is present in our course, so I have given that. So classical mechanics we are starting, and for that now we should know that what is a particle. What is a particle? So a particle is an entity. A particle is an entity of finite mass but infinitesimal small in size. So particle is an entity of that finite mass, but it will have that infinitesimal small size that we will consider as our particle in that classical mechanics. We can have the example that ball is assumed to be a particle. Okay. It is idealized only, it means that in general it will be not like it, but for the study we are idealizing the things that it will have that finite mass, but it will be that infinitesimal small in size. And we can we will consider the size in the case of that rigid bodies, that will have that other chapter. When we will move to that rigid body, now there we can't ignore that size of the particle. but there that particle will be present at the same distances, that are definite distance it will be present, and there we will have that size as well. So we will, when we will move to that, we will study those things. So this particle, idea of particle I have given to you. Now move to this very first philosopher, that is our Aristotle. Was present at the time of Alexander, great Alexander, in 322 BC, 323 BC. What happened, you know, that first we shall move to that Aristotle theory. Aristotle. What the Aristotle told, that if a body or not body, we can say that a body, we can also say that body will have that, we will consider as our particle. If an object is moving with uniform velocity, we will have the requirement, we will have that requirement of force. So he told that when a body is moving with uniform velocity, that to maintain that uniform velocity, we will have to be apply some force on it, because he saw that when are we applying force on an object and removing the force, the object stops after some time. So he saw that when we are applying some force on an object and it will start moving, and when we will remove that force, it will get stopped after some time. This was that observation of that Aristotle. He was that Greek philosopher. You will be aware about that Aristotle. From that your history chapter. So it was that Aristotle who told that to maintain that uniform velocity of the objects, we will have to be apply some force on it. First he told this thing, and he did not so Aristotle gave that idea that when that a body is moving with uniform velocity, to maintain that uniform velocity, we will have to be apply some force on it. But Aristotle did not consider the force of friction. Force of friction. So why that body is stopping? It is because of that friction he did not notice. So this theory that proven wrong by that Galileo, and we shall move to that. He defined that body is stopping because of that friction, and Aristotle was not able to notice that body is stopping because of that friction. And next we shall move for that Galileo that theory. After the Aristotle, that Galileo came. In that 1564 to that 1642 was that time of that Galileo, and he told that for a body, you may have seen this Galileo observation in your 9th class. So for a body to maintain the state of motion, no external force is required. So if a body wants to maintain that state of that motion, if it is moving, no external force will be required on it, and he proved it by considering two inclined planes. Here we are having two planes. This is our plane. This one is your plane 1. It is our plane 2, and a ball is rolling down. A ball is present here and it is rolling down because of that force of gravity. So when this ball will come down, when before it we will say that that here we will assume the friction very small, friction force is very small, or no friction is present there. So when the ball is coming down because of the force due to gravity, it will have positive acceleration. It will have positive acceleration First you can have the screenshot up to here. After that I'm rubbing upside. So when that ball is coming down, it will have that positive acceleration, and from here I'm braking and I'm starting from here, and when it is going up in plane 2, which is at some inclination, it will have negative acceleration. It will have negative acceleration. So when it is coming down, it will have that positive acceleration, and when it will go that up in that plane 2, it will have negative acceleration. And if we are making our inclination leveled, means that for leveled surface, when for level surface, this positive acceleration here, and negative acceleration here will cancel out, and for level surface, leveled surface, body having or object having no acceleration. So he performed this experiment, and you can have the screenshot up to here. From this, he told that if we are having two inclined plane, this is plane 1, this is plane 2, and it is making an angle in anti-clockwise direction alpha, it is making an angle in clockwise direction, which is theta, and body is covering, while it is coming down, body is moving with the distance of d1, and while it is moving up, it is covering the distance of d2. Here we can say that d1 is that distance traveled in coming down, and d2 as our distance traveled in moving up. So if our theta is equals to the alpha, if theta is our equals to alpha, so our d1 will be approximately same to d2, and if our theta is less than alpha, then our d2 will be less than d1, and when that theta is more than alpha, so our d2 will be more than d1. This thing he has told. You can have this screenshot. Now when alpha is equals to 0, when alpha is our 0, that d2 will become infinite. If alpha is 0, d2 will become infinite. So the ball will keep on moving. So the ball will keep on moving on leveled surface, without any external force. So he told that to maintain the state of motion we will have no requirement of external force. It was that Galileo who first proposed. Okay. So what did that Galileo observe? That observation made by Galileo was that if a body is at rest, or in uniform motion, then both states are equivalent, and no force is required, no external force, we can say no external force is required to maintain this state. Look at to the observation of that Galileo, that he told that if a body is at rest or in uniform motion, it will that have those state without until we are not applying some external force on it. So what is our Newton's first law? That if a body is at rest or moving with certain velocity, it will have those states until and unless an external unbalanced force is not applied on it. External unbalanced force will be not applied on it. It will have those states of rest or that motion. But it was that observation of Galileo, and that is why we say that law of inertia has given by Galileo. Note, in general, we will say that it's specious question as well. They can ask to you that in general we will say that law of, or in that NCRT also it is present, law of inertia is given by Galileo. So in 1642 Newton born on earth, and he piled up the theories of that Aristotle, Galileo and other ones, and gave the Newton's laws. He actually focused to the Galileo because Galileo has reached to the inertia, and in that 1642 that Galileo died. So 1642 that Galileo is dying, and Newton is that borning. It is taking born on the earth. So he will pile up all this theory and will give that Newton's laws of motion, and those Newton's laws of motion we will study in that next session. This was that session in which we have that took the idea that what is the history behind of that laws of motion, and that is very important. From there pseudo force will come, and that in so many exams you will have the question of that pseudo force, and it's not easy to that make you understand pseudo force. Still I have tried my best to make you understand, and when we have that numerical session we will have that more better that understanding of that pseudo force. So up to here, write it and that read it and try to understand, and next thing that Newton's laws of motion we shall start soon. Thank you all of you.